Vibration of air, the result of sound waves being created. Volume, how loud or soft the sound is. Pitch, how low or high the sound is. The tubes, the examples of them. The closed-ended is like the water bottle with the closed end, and the open-ended is with the water bottle that has the open end.
Okay, another example that we could use is a string instrument. So we are going to be talking about the guitar, and as Jack plays, you can tell that when he plays the thicker strings that they will produce a lower sound, and then the thinner strings will produce a higher sound. And also, when the tension is changing, depending on the string, the more tension the string has, it will produce a higher pitch. So the tighter the tension, the higher the pitch is. And also, depending on the length, the shorter string will produce a higher pitch, and the longer string will produce lower sounds. Okay, so now we are going to be talking about waves. And so the rate of a wave is called the frequency of the wave, and the rate at which the notes remain the same as the standing wave. And basically the velocity, or the speed of a wave, is the wavelength times the frequency, and that's how you can find the velocity of the wave. And sometimes an object that blocks the light or sound happens to occur, and we call that interference. And as we just showed, we showed you a transverse wave of the salt and the vibrations of the sound, and this is what that looks like. And also a longitudinal wave, which is an example of that would be light. And here is a diagram showing the amplitude, the nodes, wavelengths, and crests and troughs of waves.
Our light source is Austin Carter's iPhone, and our object is this nice pencil. And as you can tell, when the pencil gets closer to the phone, or the light source, the shadow is blurry and large but out of focus. And then when the object is farther away from the light source, the shadow is more accurate and precise.
Polarized light. Light waves in which the vibrations occur in a single plane. Color. The property of an object producing different sensations on the eye. Duality. The state of being in two parts, where the principle of wave particles is duality. Here's the visible light spectrum. It starts off violet, goes to red.
Okay, so these are two diagrams of additive color models and subtractive color models. And as you see in the additive one, in a dark room, if you were to shine a green and red light on an object, it would produce a yellow light. If you shine a green and a blue light together, it would produce a cyan color. And if you were to produce a blue and red light, you would produce a magenta color. And if you were to shine all three of these colors on an object, it would produce a white color. On the subtractive model, if you were to shine it in a white room, if you were to shine a yellow and cyan color on an object, it would produce a green color. If you were to shine a cyan and a magenta on an object, it would produce a blue or violet color. And then if you were to shine a yellow and magenta color on an object, it would produce a red or orange. And if you were to shine all three of them together, you would produce a black light.
For the convex lens, the focal point of the star was 3 centimeters away. The object distance was 5 centimeters away, and the height was 2 centimeters. The image appeared was a real, bigger, and inverted. The formula we used for both the concave and the convex was 1 over focal length equals 1 over object distance plus 1 over the initial distance of the object. The distance initial was 7.5 centimeters, and the height formula that we used was dO over dI equals HO over HI, and that equaled was 3 centimeters. For the concave lens, the focal length, object distance, and the object height all were the same as the convex, besides the object distance was -5. The formula was the same for both, and the DI was -15 over 8 centimeters, and the height was 3 over 4 centimeters. And as well, this one was virtual, upright, and smaller.
Okay, here are some more images that were produced using concave mirrors and convex mirrors. Over here on the left, on the concave mirror, we used a triangle as our object, and we used a focal length of 4 centimeters, and the object distance was 6 centimeters. And we produced a real inverted and bigger triangle, and we were able to find the triangle's distance by using the formula here. And then also on the right, the convex mirror, we produced a real inverted bigger image using the same focal length and object distance, and we found the image's distance by using this formula as well.